Hi and welcome back to class of Design of Machine Elements. I am Hitesh Raiyani, Assistant Professor at LJ Institute of Engineering and Technology. This is lecture 36, Design of Helical Springs. The learning outcomes of this lecture is to learn how to design the helical spring subjected to static loads. So consider one problem here. It is required to design a helical compression spring subjected to a maximum force of 1250 Newton. The deflections of spring corresponding to the maximum force should be approximate 30 mm. The spring index can be taken as 6. Here the spring index is given, that is capital C is equal to 6, and approximate deflection is given, that is delta approx is equal to 30 mm, and the force P is applied, that is 1250 newtons. Now the spring is made of padded and cold drawn steel wire. The ultimate tensile strength and modulus of rigidity of spring material are 1090 and 81370 Newton per mm square respectively. The permissible shear stress for the spring wire should be taken as 50% of the ultimate tensile strength. So here you have to consider the permissible shear stress is equal to 50% of the ultimate tensile strength. So permissible shear stress is equal to 0.5 into SUT. Now you have to take. Now design the spring and calculate first wire diameter, mean diameter. Third is number of active coils. Fourth is the total number of coils. Fifth is the free length of the spring, and sixth is the pitch of the coil. Also you have to draw a neat sketch of the spring showing various dimensions. So in this case you have to design the spring according to the given conditions, and also you have to calculate the wire diameter, mean diameter, number of active coils, number of total number of coils, free length and pitch of the coils. Also you have to draw the spring according to calculated dimension at last. So consider these problems. So according to these problems, the given data is P is load is applied 1250 newtons, delta approx is given 30 mm, spring index C is given 6, SUT ultimate tensile strength is given 1090 newton per mm square, and tau is equal to given 0.5 SUT. So first step we have to calculate the wire diameter. So to calculate the wire diameter we have to use the equations of shear stress, and for that we have to first calculate the tau is equal to 0.5 into SUT. Here the condition is given, tau is equal to 0.5 into SUT, and value of SUT we have 1090 Newton per mm square. So if we place the value of SUT, we get the tau is equal to 545 Newton per mm square. So this is the tau. Now also we need value of K, that is the van der Waals factors. So K is equal to 4C minus 1 divided by 4C minus 4 plus 0.615 divided by C. Here C is given 6, and you can calculate by placing the value of C. So K becomes 4 into 6 minus 1 divided by 4 into 6 minus 4 plus 0.615 divided by 6. So we get the value of K, that is Waals factor, that is equal to 1.2525. Now we know the equations of tau or shear stress, that is equal to K into 8pc divided by pi d square. Here the equation in terms of spring index, so it will be K into 8pc by pi d square. Here C is given, B is given, small d we have to calculate, K we have a value of 1.2525 and tau we have 545. So if we place the value of all these things, we can calculate the small d, that is the wire diameter. So by placing these all value, we get the equation like this, and if we simplify these equations, we get the small d, that is wire diameter is equal to 6.63, or you can say the 7 mm. So this is the wire diameter 7 mm. Now step 2 is calculate the mean diameter. As we know, the spring index C is equal to capital D by small d. So by using these equations, we get mean diameter capital D is equal to C into small d. Here C is given in our problems and D we calculated in previous slide, and that is equal to 7 mm. So if we place the value of capital C and small d in equations of capital D or mean diameters, we get mean diameter is equal to 42 mm. Now step 3 is the number of active coils. So for that we have to use the equations of delta, that is deflections. Here the approximate deflection is given, that is 30 mm. So delta is equal to 8p d cube into capital N divided by GD raised to 4. Here capital N is the number of active coils, and we calculated capital D and small d, and also P is given in our problems, P and delta is given in our problems, and G is nothing but the pi by 32 raised to 4. So if we place the value of this, also here the G is given, that is 81370. So delta is equal to 8 into 1250 into 42 raised to cube into capital N divided by 81370 into 7 raised to 4. Here delta is 30. If we place the delta is equal to 30, so only unknown is the capital N, and we get the N is equal to 7.91, or you can say the 8 coils. So number of active coils is the 8. Now step 4 is the total number of coils. So how many number of total coils we have to calculate? So it is assumed that spring has square and ground ends. So number of inactive coils for that is 2. Therefore the total number of coils NT is equal to N plus 2. Here N we calculate, that is 8. So 8 plus 2 is equal to 10. So total number of coils is equal to NT is equal to 10 coils. Now next is the free length of the spring. So we have to calculate the free length of the spring. So as we know, the free length of the spring is equal to solid length plus deflections. So we have to calculate first the actual deflections of spring is given. So here delta is equal to 8p into d cube into N divided by GD raised to 4. So to calculate the free length of spring, we first calculate the actual deflections in spring. So here we have to put the all value P is equal to 1250, D is equal to 42, N is equal to, we take here the 8, and G is 81370, and the small d is 7. So we get the delta is equal to 30.34 mm. That is the actual deflections, that is equal to 30.34 mm. Now solid length also we need for to calculate the free length. So solid length of spring, as we know, that is nothing equal to the total number of turns into the small diameters or wire diameters. So it is equal to NT into small d. Here NT is 10 and small d is 7. So the solid length of the spring is 70 mm. Now assume the gap is equal to 1 mm. So here the total axial gap becomes, as the number of coil is 10, so hand gap is 1 mm, so it will be 10 minus 1 into 1, so the total axial gap is 9 mm. So we know the equations of free length is equal to the solid length plus gap length plus deflection. So we can calculate the free length now. So free length of spring is equal to solid length plus total axial gap plus delta. So here we calculate the solid length in previous slide, that is equal to 70 mm, total axial gap is 9 mm, and deflections of spring is 30.34 mm. So if we place all this value, we get the answer of free length is equal to 109.34, or you can say the 110 mm. So this is the free length, our required answer. Now pitch of the coil. So as we know the pitch of the coil, so pitch of the coil is nothing but the free length divided by total number of coils minus 1. So here the free length we calculate here, and that is equal to 109.34, and NT we calculate, that is 10. So if we place the value of free length is 109.34 and NT is equal to 10, we get the pitch of coil, that is equal to 12.15 mm. So now next is what we have to draw the string diagrams according to the our calculated answer. So we have to plot at the end the spring with our calculated dimension. So here you can see the spring of spring with dimension we calculate here. So here the 7 phi is the diameter of wire, length of spring or free length of the spring is 110. Here the pitch is 12.15. So mean diameter is 42. Mean diameter is 42. So the inner diameter is 35 and outer diameter is 49. So this is the final string diagram according to the given problem. So in these lectures we learn the design of spring when it is subjected to external static force. Thank you.